Everyone thinks they understand gravity, but we don't. Not really. Drop something and it falls, planets orbit, moons spin. Simple. Right? What if I told you that gravity isn't actually a force at all, but the bending of reality itself? This is the story of how one man, sitting in a small Swiss office with nothing but a pen and a brain that refused to stop, rewrote the universe. It's the late 1600s. England is still recovering from Civil War, candles light the streets, and a 23-year-old named Isaac Newton is sitting under an apple tree. At least, that's how the story goes. But what really happened that day changed science forever. When the apple fell, Newton didn't just ask why it fell, he asked why the moon didn't. He realized the same force that pulls an apple to the ground might be the very same thing that keeps the moon in orbit. That was a wild idea at the time. The heavens and the earth were thought to obey different laws, but Newton broke that divide. He proposed something revolutionary. Gravity was universal. He imagined every object in the universe, from pebbles to planets, pulling on every other object with a force proportional to the masses and inversely proportional to the square of their distance. Mathematically, it was beautiful. With that simple formula, Newton unified the cosmos. He explained falling apples, orbiting moons, and the paths of comets across the night sky. For over 200 years, his law worked perfectly. Every test, every measurement, flawless. Until it wasn't. By the 19th century, strange things began to appear in the math. A tiny planet, Mercury, wasn't obeying the rules. Its orbit shifted ever so slightly, by just 45 arc-seconds per century. Minuscule, but undeniable. Astronomers were baffled. Some thought there must be another planet tugging on Mercury. They even named it Vulcan. But no planet was ever found. Then came the question of light. If gravity was a force pulling on mass, why did light, which has no mass, bend around stars? Newton's universe was solid, predictable, but cracks were forming. And somewhere in Switzerland, a young patent clerk named Albert Einstein was watching those cracks widen and wondering what lay beneath. Einstein was 26, broke, and working a desk job, reviewing patents for electrical devices. One morning, as he stared out the window, he had what he later called the happiest thought of his life. He imagined a man falling from a rooftop. To that man, everything around him would appear weightless. The coffee cup beside him, the papers falling next to him, all floating together. That simple thought led Einstein to realize something profound. Free fall isn't the absence of gravity, it's the experience of gravity itself. And from that insight, he began to build a theory that would shatter Newton's picture of the universe. Einstein started by asking, what is space? What is time? Before him, everyone thought of them as two separate, absolute things. A cosmic stage where the universe events simply played out. But Einstein saw something deeper. That space and time are intertwined, forming a single four-dimensional space called space-time. Mass doesn't sit in space-time, it warps it. And that curvature tells other objects how to move. It wasn't that the Earth feels a force pulling it towards the sun, it's that the sun bends space around it, and Earth simply follows the curved path. As physicist John Wheeler later summed it up, mass tells space-time how to curve. Curved space-time tells mass how to move. Einstein had replaced Newton's invisible force with something even more elegant, geometry itself. But could this strange, beautiful idea actually be true? In 1919, an opportunity appeared, a total solar eclipse. Einstein predicted that the light of the stars passing near the sun would bend, just slightly, by 1.75 arcseconds. British astronomer Arthur Eddington set out to test it. During the eclipse, as the moon blocked out the sun's glare, he photographed the stars beyond. And when the images were developed, there it was. The starlight had shifted, exactly as Einstein had predicted. When newspapers around the world printed the headline, "Light all askew in the heavens," Einstein became a global celebrity overnight. His theory didn't just work, it redefined what gravity even meant. But here's where the story gets even stranger, because if space can bend, then so can time. Einstein's equations predicted that the closer you are to something massive, the slower time flows. Clocks tick slower on the surface of Earth rather than in orbit. Your watch is running a few billionths of a second behind your GPS satellite, and your phone has to account for that just to tell you where you are. Time is not just universal, it's relative. And near a black hole, time nearly stops. Hold that thought. When a massive star dies, it collapses under its own gravity. The collapse doesn't stop, it accelerates, crushing matter into an infinitely dense point called a singularity. Around it lies a boundary, the event horizon. Beyond that, nothing, not even light, can escape. Einstein's theory predicted these monsters, but even he doubted they could even exist. But they do. Black holes are real. They are the most extreme object in the universe, where space-time itself tears apart. For decades, black holes remained invisible. Stars whipping around something unseen, radiation from invisible giants, but never the thing itself. Then, in April 2019, the impossible happened. A team of 200 scientists linked telescopes across the planet, forming a virtual Earth-sized observatory, and captured the first direct image of a black hole shadow in galaxy M87, a glowing ring of fire around a void so dark it defied comprehension. It was Einstein's vision brought to life, a century-old theory proven by a picture. So, what is Einstein's theory of general relativity? At its core, it's not a theory about equations or stars, it's a theory about how the universe shapes itself. Imagine space-time as an enormous invisible fabric, stretching across everything. When you place something massive on it, like the sun, the fabric curves, and that curve is gravity. Planets aren't just being pulled, they're falling endlessly along those curves in space-time, just like a marble rolling around a dent in a trampoline. But in 4 dimensions, where both space and time bend together. And this bending doesn't just tell objects where to go. It tells light how to move, time how to flow, and reality how to behave. It means that what we call gravity isn't a force reaching across space. It's space itself changing shape. General relativity is the rulebook for this shape-shifting universe. It explains why planets orbit, why light bends, why time slows down near massive objects, and it's been tested over and over and over again, from orbiting satellites to colliding black holes. Every experiment has said the same thing. Einstein was right. Not because he guessed correctly, but because he understood that the universe doesn't pull, it curves. What makes Einstein's story so powerful isn't just the math, it's the imagination. He doesn't have fancy equipment or billion-dollar telescopes. He had thought experiments. He asked simple, almost childlike questions. And from those questions, he uncovered truths about the cosmos that still guide us today. Einstein once said, "The most incomprehensible thing about the universe is that it's comprehensible." And maybe that's the real legacy of relativity. Not just bending space and time, but bending our understanding of what humans can imagine. You don't need a lab, or a $1 million telescope, or a genius title to change how the world sees itself. All you need is curiosity and the imagination to ask questions that haven't been answered yet. So, if that part of you, the curious part, wants to keep exploring, then subscribe and don't stop asking questions.